So now that we've done diprotic systems, we want to extend this to polyprotic systems. If we have 3 or more protons as part of our system, how do we deal with the different situations? So we'll just go one more. We'll go to a triprotic system, and we'll see sort of the general principles that apply even as we go to larger numbers of protons. Okay, so one example of a triprotic system is phosphoric acid. Phosphoric acid has 3 different protons to be lost. And what we're going to do to find the pH values and to look at the equilibria is identify what type of molecule we're looking at. So we have with phosphoric acid, we have multiple different options so we have the fully protonated form here. We can lose a proton and form dihydrogen phosphate. We can lose another proton and form hydrogen phosphate, or we can have the fully deprotonated form that's just phosphate. So now we have 4 different species we can look at. And how we approach each of these depends on which of these we're looking at. If we want to find, solve equilibria involving the fully protonated form, phosphoric acid, just like with the diprotic system, we would treat this like a monoprotic acid. So we use the same approach where we'll end up with x squared over f minus x equal to the Ka, and we would use Ka1 to solve this equilibrium. If we have the fully deprotonated system, phosphate, we treat this like a monoprotic weak base. And here we'll use Kb1, which, just to remind you, will be equal to Kw over Ka3. Because now we have 3 different possible Ka values. Kb1 is going to correspond to that last Ka value. All right, and then for our 2 intermediate species, we use the derived equation. And what I mean by that's the equation that we spent a long time deriving, where concentration of H plus is approximately equal to square root of K1 K2F plus K1 Kw over K1 plus F. The only tricky thing here is that you need to keep track of which K values to use. So I have 1s and 2s here, and it's going to depend on which intermediate species, which K values you use. So if, for example, we're looking at H2PO4, dihydrogen phosphate, our K1 will be Ka1, our K2 will be Ka2. And then it'll just depend on the concentration we have. If instead we're looking at hydrogen phosphate, now our 2 relevant K values are for the 2 acids present, the H2PO4 minus and HPO4 minus. So K1 will instead be Ka2, and K2 will be Ka3. So that's the only tricky thing with polyprotic systems. You have to keep track of which species are present that you're needing to consider. But otherwise, yeah, we treat this just like we did the diprotic systems. So in the next video, we'll go through some example calculations for phosphoric acid, looking at their Ka values to find the pH of concentration, a specific concentration of each of these.